Well, hello and welcome to the 36th podcast. Made it this far, and I keep finding subjects to talk about. So I guess that's a good thing. In any case, we today, as I talked about in the last one, we're going to discuss acoustic imaging, in particular as it relates to partial discharge testing. Now, we'll do something on leak detection in a future one because I don't want to confuse it too much. The other thing is there are detectors or acoustic imagers that were put out, primarily, I believe the first ones I've seen came out somewhere after 2021, probably 2022. And of course, hit the market, like a storm, primarily for leak detection, and then within certain ranges for partial discharge and other acoustic detection. So let's get into a few things first before I talk about the instrument I got my hands on, which basically the price range on these have run, well, for acoustic imaging, run somewhere about $7,000 to $40,000. And the PD versions will run anywhere from about $9,000 to, again, about $40,000. So when you get up in that range, above $30,000, you're generally finding the combined units. The other ones, as you get lower in price, appears to have some variations in capability. However, also includes some purchasing and brand name, right? So I got an off-brand. I got one of the about $9,000 units. And there's some features I'd like to have in it that are displayed or talked about by the higher cost technologies. If I was using this every day, I probably would have gone with one of the higher cost units. Now, there's a lot of interesting things that go along with partial discharge acoustics. Now, it's not anything new. The acoustic partial discharge detection goes back to the 1970s. Anything from detecting issues in high power lines to detecting issues with partial discharge in transformers, connections, electric motors, things like that. Not used that often in motors and generators, smaller ones. But now with the cost coming into an area, or more so, the concept of the new acoustic imagers, that's a little bit better. Now, if you want to go in depth, and I'll talk about some of the ranges, but if you want to go in depth, there's an excellent book called Practical Partial Discharge Measurement on Electrical Equipment. I know all of the folks that are on here. We serve on some of the same committees. They're all the people that are writing the standards, both national and international. In any case, starting on page 97, they specifically talk about acoustic partial discharge and acoustic imaging. Now, there's a couple of things that are specified in the book, and we've talked about in some of the standards meetings, and that is that you have to have a range that goes up to 100 kilohertz. That means you have to have a camera that has a frequency range from about 0 hertz up to 100 kilohertz. Now, normally with leak detection, you're going to be somewhere, maybe 50 dB, maybe a little higher. The camera I got is a 65 dB for leak detection with a switch to change it to 100 kilohertz for the higher end. Now, just as I showed in the last video, I showed you the HIKMICRO Infrared, which also runs similar in price to a FLIR of the same type. So somewhere around $600. This is the $9,000, $8,999 HIKMICRO AI56, and we'll talk about this a little bit more. But after I take off the cover, one of the things you'll note is all these holes here. Those are all of the locations for the sensors, and then there's a camera in the middle. So it'll take color video and everything else. This has 69, I believe it's 69 sensors. And then when you get up into the Fluke and FLIR and some of those guys, they start at about 128 sensors, which gives them a better resolution and a few other conveniences for PD. Now, because I don't do it that often, if I'm going to do it, it's probably going to be on stators or in a cabinet. You have to remember when you're looking at acoustic imaging, just like any other, infrared and so on, you have to worry about noise reflection in this case. So I could be looking at something and it could actually be a reflection off a wall or something else. So the other ones that have the higher number of sensors claim that it is easier for you to determine the correct direction. This one is supposed to be a little more challenging. There were some things we learned, some things we did, and you know, I'll go through it a little bit as we go through some of the software. You can see the software wherever the software is above me or to the side. In any case, free software runs on your local PC. There's no cloud. There's no AI. There's no anything else. So let's take a look at it. Now I have it set up for PD. A lot of the other cameras, they'll have the range and everything, but they, for whatever reason, separate out the software. So you can buy a leak detector and it's the same system, and then you pay more to get the partial discharge detection. The one thing I liked about the AI56 is I have both. So the big trial was, did it work? And that's a big question. Did it work? And I'll show you some video, and we'll talk about some of the other stuff. It's pretty intuitive, thank goodness, because the manual, to be blunt, sucks. Or what manual, I should say. The only thing in the included documentation, which it looks thick, was actually more along the lines of pointers to show you what everything was. Some conveniences, the charging port, there's an SD card port for micro SD. There is a USB-C port for charging, but also for communications. And then there's an HDMI port, so you can connect it to a much larger screen, which we'll do when we do the acoustic for leak detection on the next video. So, yeah, I think we'll do it on the next one. There's some things coming up that I think we'll have a lot of fun with. Other things with this came with all the cords, straps. It came with a total of 3 batteries, one in the unit and 2 separate ones. And then the charger. Each one is supposed to last about 3 hours. I've had no problem. I was at the repair shop. We were doing the stator that you can see one bit of it in this. You can see the stator here, but in any case, yeah, the part of what we were able to do is I just kind of left it on and set it on the bench, and we were doing 2.5 hours worth of testing, and I still had a lot of battery life. Matter of fact, when I uploaded everything, I just left it plugged in and let it go. So when I show you some of the stuff, the dates are a little off. I think on some of the first ones, whoops, I just took an image. But that's fine. I fixed that for the study. Things on here are the menu. I've got the cover back on so you can't see the background, but I have this zoom in area there. When I get rid of it, it allows the field of view to broaden. I like keeping it focused in for what we were doing. I have a little bit of both. This one here turns on and off the detector. You'll see it says noise up top right now, so it's telling me everything. The background is noise. As it gets into Corona, which I will show you Corona in a video, that will just switch over and it'll determine low, medium, and high corona. High corona. But neither here nor there. I have it switched for PD right now. Another inconvenience I ran into was some of the other ones claim that what they do is they will automatically determine the distance to what you're testing or to the defect. You have to go in and set the distance. So I'd have to go into the menu, and then there's a bunch of stuff I can do. I can change the sensitivity, keeping it in 3, frequency ranges, which allow me to zoom to different frequency ranges. Then I can move this up and down, of course, when I get out of there. The distance in feet. This gives me access to the thing so I can actually play the recordings right on here. And then all the settings for setting the device. Yes, it does have Wi-Fi, it does have Bluetooth, it can connect to an app. I'm not using the app, I'm just using the other stuff. So let's get back here. And with that, I'm going to stop talking so much about this. Again, we'll talk about the leak detection capability and how accurate it is on calculating energy losses next weekend after I get a chance to play with that part of it. Going to have more fun. But overall, pretty robust. It's not something I'm going to throw around, but I mean, it's a solid, hefty device. It did everything it was supposed to do. That was the key. I wish it would allow me to put my own logo in it or in the software for the reports, but that's the same thing I ran into with the camera. It's possible that there's somewhere in here that'll allow me to do that for the reporting. I just haven't found it yet. Okay, so here's the software here, and it's going to allow me to do all kinds of stuff and make changes and so on and so on and so on to what I'm reporting. So now we've had our look at that. Let's talk a little bit about the PD. Now, so when I'm looking at partial discharge, I look at a couple of different things. One is what we'll refer to as a high-frequency partial discharge. That is the partial discharge detectors where you're using the RTD or you're using a capacitive coupler, usually a 5 or 10 picofarad coupler that's connected to the leads of a motor or generator in order to detect PD or partial discharge occurring within the winding in a stator itself or in some other device. You can do it for cabling, and you can do it for transformers, and on and on. I'm going to stick with just the electric motor because of the subject we're doing here, but I can do it pretty much with anything. So in any case, partial discharge is going to be a series of peaks that occur that are sound impulses at relatively high frequency. And we, as human beings, will tend not to hear it in its early stages. It'll be higher up. The optimal stage, according to the book and according to what we're discussing in standards, is about 40 dB. So for acoustic, for a regular detector like the capacitive coupler or the RTD style, you're talking about much higher frequencies in the megahertz, gigahertz, and so on in order to detect it. It's an amplitude modulated signal, so it's an AM signal. As a matter of fact, it used to be that you could take, you still can, an AM radio and scan through and look for noise. Which also means, by the way, that you can run into situations where a radio station will interfere with your PD detector and can cause problems because you use an antenna to detect that. The next one that we haven't talked about yet is UV, or your corona cams. Those tend to be quite expensive. They're UV cameras, and they're kind of like infrared, but they look in the UV spectrum. So when we tested this, we did that. The funny part was somebody had left a door open, and so on one side of the stator, They went, oh my gosh, we've got, PED. Well, no, we didn't. I mean, we were doing both, an iris power engineering partial discharge offline PD detection coupled with the UV or Corona cam coupled with this device. So I wanted to test it. So we did a couple of things. First off, I did some testing in the field before I got there. I'm going to show that in the videos first. The second thing is during the AC high pot test on this 13.8 device, we were able to see corona, as a matter of fact, high corona discharge while we were monitoring it. I did that deliberately to see if it could detect it. And then finally, we went ahead and did PD detection. Now, nothing detected any PD. We did see an odd signature right about 65 hertz, 64, 65 hertz, which I believe we'll see in here maybe. Yeah, here it is, right around 62 hertz. This was interesting. At first, I thought it might be some level of partial discharge, especially see the ladder. But as it turns out, that was present even when the stator was disconnected and uncoupled, so we didn't worry too much about it. This is the view that we're using for identifying it. You can see this is all pretty random, and then of course this is the live signal here. I haven't figured out how or if I can export it yet. If I can, I'm going to play a little bit with Python and go in and see if I can do different things to play with this FFT here. So this signal here, this is the range that it's looking for PD. This is some other stuff. There's an intensity range here, so I can make things worse or better. I can get rid of all the noise, but in any case, we're at a pretty low range. It's not identifying anything. This is the part I'm trying to figure out right now, and there's really not much out there on it that I've been able to find yet. I will report out on that separately. But how are these cameras determining levels of partial discharge and values? Couldn't find it in the textbook. I am going to look up some papers on it, and then we'll talk about that then. So let's get into the rest. First, I recently watched a video on this while I was determining whether this is a service that we wanted to participate in. And I noted a couple of things that were really interesting by salespeople / technical folks / mechanical engineers doing electrical stuff. And in one case, I found it really interesting that somebody said, a corona, that just occurs on the surface around it. It's not surface corona, so you don't have arcing or tracking going on. Corona happens in the air around an object, and it's completely harmless. It's just noise, which is absolutely false. One of the problems with partial discharge overall is the generation of ozone. Even in corona, you have ozone, and that ozone chemically attacks the insulation system. So when you do have partial discharge, whether it's corona, surface tracking, slot, or whatever else, it will actually cause damage over time. It's not immediate, and it is in some ways an early detection of things. Now, when I get into cabling, that's also a problem, and I'll usually see with cabling and conductors problems right where joints occur, usually splices and the like. That is often contamination related. And then when I get into transformers and the like, PD is basically arcing. So it's tiny little discharges, buildup of energy and then discharges, and maybe a micro arc or something like that you might not even be able to see, or may be significant and high enough that you would see it. So what we're doing is we're listening for that that sound associated with those discharges. Again, The area we want to the optimal area is right around 40 kilohertz on a Corona or I'm sorry, on a acoustic imager. So before we get into looking at some of this stuff here, let's look at some videos and take a look and see what we can see. And I'm going to go back because the dates are a little mixed up here. And let's see if we slow the system down. So when I went out to the job site, I saw some towers, and then I discovered there was a big distribution center nearby. I figured that would be a great place to start. Took forever to get over there, well guarded and everything else. I will not talk about where it is. I think you can set it up so that the camera will tell you where you are. I'm not going to do that in this case. And I don't know if there's sound. I know that it takes audio. So if there is, then yeah, matter of fact, I can hear it. So I've left off the computer sound, but I'm scanning back and forth here. I'm allowing it to auto-detect. I haven't scanned up and down here. I'm not seeing any particular frequencies. And you'll notice up here, if it was partial discharge, corona, or whatever else, it would say it up at top. But I'm just scanning around the yard. It's telling me anything I'm seeing is basically noise. Now I've got the sensitivity set a certain way, and you notice this little button here is off. All this stuff down below, that's road traffic. I'm right next to a highway nearby. If I had a UV camera and I was looking for that, well, I'd have some problems because I'm out in daylight. So that's the first video. Let's take a look and investigate the next one, which same site. And there may be some delays because, of course, I'm running multiple things in the background as I do. Okay, so let's go ahead and replay this one here. More of the same. It's telling me noise. Now, I didn't zoom in, I didn't use this part here, and I didn't look particularly for stuff. But some of the reasons it's bouncing around is because I have this highway noise. I just wanted to get up here close to the 100 kilohertz at the top, just to see if I see anything, and it's bouncing all over the place. So really my optimal view is down here, but I would notice in this spectrum on the right. Now, here's what's interesting. The FLIR and Fluke cameras have very similar layouts. So I would see it primarily here. Again, this is all traffic. I would be looking for PD up here for this one. So let's go on to, we'll give this a second to catch up. Okay, so I thought I had a video of this particular one, but let's go ahead and we're going to see one of the things that we were looking at. And this would be, I believe, some level of corona. Let's get here. This is the good one. Okay. There's our good corona scan. You see the choppiness here, but you can also see the FFT. You see that we're, in a pretty good range, and things are a little more defined, and it's a raised noise. It's a raised floor. So that is corona occurring at that spot. It's saying 99%. Now this, as I mentioned, this is, one of those things where I want to know how they're determining it, and we will see as I find more information. There was some other things like this is where I was trying it out, testing it before going in the field, and discovered certain things with when you make the settings, you have to make sure you hit OK for it to enter, because if you hit the back button and go back, you think you've entered everything in, you really haven't. So let's, yeah, it doesn't give me anything more. Okay, and I can't widen that out. Can't make these any bigger. So let's go ahead now, and we are going to take a look at some data here. And I believe this one would be the last one. Looks like it, yeah. So this is the last one. So this one is taking some background noise, just to see what's going on. So we see these peaks here. This is the first one I was showing, the last one. These peaks were still there. It's telling me 0 on everything. You can see I set, by the way, 5 feet. I've got this frequency set up a little higher, primarily because these spots go away as I reduce. So if I come here and I make this higher, you'll see they get smaller. So I can zoom kind of in on where these frequencies are. And it looks like it might be corona or discharge, but really it says it's noise. And chances are these are reflections from somewhere else. But we'll watch the video. So this is de-energized. So I have these peaks here. So, okay, those exist. So let's take a look at the system when it's running. You can see very, very similar peaks exist. That signal is there. I'm in this about the same range. It's still calling it noise. Let's take a look on the other end. So this is the connection end, right? Yeah, there's our connection end. That peak, those signals are not there. So you have to remember, sound is very directional. It does reflect. It does some other stuff. Again, look, see, just about 1% it's claiming. That's, well, I didn't see it there. So about 1%, that's actually a thing. Especially where we were 2% there. That would be on the first phase test. Let's see if we see anything here. Again, 2% right out here. 0%. Okay. So very interesting. There's the peak. Okay, you can see that I've got a peak right there. That's my 2%. So that's going to be the PD associated with this spot right there. Very, very interesting. Most of the other stuff, and I'm wondering also, could it also be, because you can see this little spot here, there was grinding going off to the one side. We'll probably be able to hear a little bit of it in the next part. So let's go ahead and let's take a look at some video associated with this stator. So the first ones, we'll start early, about 7 a.m. Oh, that's right. Yeah, I had some time issues. Okay, I'm going to pause again. Okay, so in this case, I'm going to be going around relatively quick. Same end as the other one. Here, I was talking in the background. Probably hear the grinder a little bit too. So this back here is from a grinder that's being run, and you can see that 60-ish hertz, 62 hertz peak showing up here on the right. Now that we again had gone through and we went ahead and tested while everything was de-energized. So let me see what we want to take a look at next here. So I'm going to pause again. Okay, so as we continue, I'm not sure because I've turned off the audio from the computer, but let's go ahead and we'll take a look. Here's a scan while we're going around. Again, you can the grinding going on the background is here. You can see I'm not showing anything on this end. That'll change when we go to the other side.
Yeah, I didn't see anything in the AC high pot either.
And then you hear me mentioning the AC high pot. Well, The AC high pot was very important because I'm expecting a massive amount of corona. So as you go through, now again, on the right-hand side, you see that 62 hertz-ish signal, and you see this all dancing around. Another thing we did is we went ahead and did the testing while we were doing the high voltage surge test. So 13.8, so we were at basically 27,500 volts on the surge test. Yeah, it's just me looking for what's causing that. So let's go ahead and I'm going to find one of the other one. So in this one, what we're doing is an AC high pot at, again, about 28,000 volts. We are absolutely expecting to see corona. As a matter of fact, the corona starts just a little over 15,000 volts as low, and then it gradually increases to high corona. Now, the high corona reading or the corona readings have to do with surface discharges on top of things. Now, it's extremely humid in there, so I was expecting it to be pretty audible. We got up to higher voltages. Again, if this was an operating in normal conditions, I would be very concerned, but we're not. So I'm not sure if you can hear it, but I will go ahead and. So I wasn't aware that I was taking sound at the same time, which is nice. But you can see all of this, and you can see all of the little movement there. Now, what I should have done is taken a snapshot, stop the video and taken a snapshot of a couple of things so that we could go in and explore it a little bit, but I did not. And if you're able to hear it, you hear kind of a bacon sizzling noise in the background. That's corona. Okay, so if you walk up to switchgear and you hear bacon sizzling, that's a bad thing, because if you try to open that cabinet, you might be the bacon sizzling. Okay, so I'm going to pause here and we'll find one more. I want to find the thumping. Actually, this next video is going to be excellent because this is during the AC high pot. Let me get this back to the beginning. And you'll see it showing noise here and low levels. Now they're bringing it up. I believe we are at 10,000, 15,000. You see the levels coming up. 20. So as soon as we hit 20,000, you can see the corona hits high. That's right now surface discharging and air braking down with an AC 60 hertz high potential test. Okay, which is a test we're going to hold for about a minute, and the idea is to see if it breaks down. It's at 27,500 volts. Twice the voltage plus 1,000, basically. Again, sizzling like bacon in the background. But we didn't see this until about 20,000 volts. So very, very important for me, because we're not seeing it here, because that means that the when we did do the partial discharge offline test, we want a value to be above the operating value, the inception voltage for partial discharge. We want that to be well above the operating voltage of the machine, so that we're not getting partial discharge or even corona at those levels. So this insulation system was built up a little bit because for specific reasons having to do with the application. So again, I'm going to look for, I really want to find the thumping. There we go. I think this is it. We'll find out in a minute. Let me pause this so it opens. Okay, again, in this case, in determining the difference between the two, let's take a look. Now, you'll notice that there's a very sharp peak right here. All this other stuff is going to be pretty steady, and then you're going to see kind of a shadow bump, bump, bump on a regular basis. That is actually a thumping noise you hear that occurs when your surge testing goes to a high value. You'll get discharges across the system to ground, which are perfectly normal, that make us kind of a thumping noise. Deep thump, not a crackling or an electrical noise, but actually sounds like a mechanical thump. So let's go ahead and we're going to play this, and then you'll notice here, so the shadowy bit, that's the thump, 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 and then this bit right here, and then all the rest of this is grinding going in the background. But that peak right about 32 hertz, that is going to be related to the surge comparison test itself. So you notice up here, not a lot going on. A little bit of stuff here, but basically while they're doing the surge test, we did all three phases. Everything went fantastic, of course. But just so that you get a chance to see that in action. And then you're seeing, as this is bouncing around, different reflections in different spots. This is your overall. So in any case, that is a quick look at our first exploration with the AI56. I've got a lot more coming, and we'll get a chance to see some of that as we continue forward in this journey. Let me see the reason I took this one. Oh yeah, there's that 60 odd hertz reflecting off the wall back here. I wasn't sure if it was the capacitive couplers on the side or if it's one of these testing devices. But in any case, that should do it. And next week we'll come back and we will take a look at this from a leak detection standpoint, doing the usual squirt bottle type thing, maybe some other cool little tests on a big screen so you can watch what's going on the screen live while we're doing it. So with that, have a great week. I hope you in the U.S. had a good 4th, and those from Canada had a good Canada Day. And we will see you next week.